Welcome to this lesson 5.1, Log Properties. In this lesson, I will tell you when to pause and write down what's on the screen, but I also want you to pay particular attention to what I say and note anything that you think might be important. The first thing we're going to do is look at how you find the inverse of exponential functions. Now, the inverse of exponential functions are always log functions. They operate a little bit differently than the way you were taught in the past. Let's take a look. Suppose you have an exponential function, x is equal b to the y. Well, the inverse of that is y is equal to log base b of x. Now, note the colors. We have done something here. The exponent y of the original exponential function becomes the value of the log function. We move that to the other side of the equal sign. The base of the original exponential function becomes the base of the logarithm. And the value of the original exponential function becomes the argument of the log function, or other words, the input to the log function. Now, I've color-coded this so that you can see what goes where. You literally rearrange each item in the expression to come up with the inverse. So let's look at some examples. If we started with 2 to the 6 is equal to 64, well, then we would move the base of the exponential function to the base of the log function. The value of that exponential function, which was 64, that becomes the input to the log function, and the exponent goes on the other side of the equal sign from the log function, and it becomes 6. Let's take a look at this one. 5 to the negative 2 power is equal to 0.04. Well, the output of the exponential expression becomes the input of the log function. The base of the exponent is also the base of the log, and the exponent becomes the output of the log function. And finally, let's take a look at the case you will see most often, and that is when it really is a function. In other words, the exponent is a variable. So in this case, our base is 2. That becomes the base of the logarithm. The output of the exponential function is 81. That becomes the input of the log function, and the exponent itself goes on the other side of the equal sign. Now pause now and make sure that you have this example, these instructions on how to rewrite exponentials as logs written down, and that you have all of these examples written down. You can also go the other direction, that is log to exponential. That should read log to exponential. And it works very similarly. Suppose you start with a log function and you want to get to an exponential function. Well, the exponent, the output of a log function, becomes the input of your exponential function. The base it becomes the base of the exponent, and the input of the log function becomes the output of the exponential function. Now here is a drawing of what goes where. Let's look at some examples. Suppose you started with log base 10 of 100 is equal to 2. Well, the base 10 becomes the base of the exponent, and the output of this expression becomes the input for this exponential expression, and the input of the log expression becomes the output for the exponential expression. Same here. We had a base of 7, so we have an exponent with a base of 7. The output of our log becomes the input of our exponential expression, and the input of the log becomes the output. And last, let's take a look at this, because sometimes things could involve fractions or negative numbers. So we had a log base 8, so we have an exponential with base of 8. Our input of the log was 0.1205. That becomes the output of our exponential expression. And the output of our log expression was -1. That becomes the input of our exponential expression. And again, yes, this should read log to exponential. Pause now and take notes of everything on this screen. Now, there are some special properties of logarithms that I want to go over quickly right now. They are related to special properties of exponents that you will recognize. For example, you know that b to the first power is just b. Well, the same principle holds with logarithms. If you have log base b of b, in other words, the base and the argument are the same, it is always equal to 1. Now, here are a couple of examples. 10 to the first power is equal to 10. Likewise, log base 10 of 10 is equal to 1. And log base 5 of 5 is equal to 1. So no matter what the base and the argument are, if they are the same, it's always equal to 1 for logarithms. The other one, I know that you remember, is b to the 0. Anything to the 0 power is equal to 1. Well, this is that property in logarithmic form. If you have log base b of 1, it really doesn't matter what the base is. It could be 9,037. If the argument is 1, that logarithm is equal to 0. Now, here are some examples. Pause now and copy these examples. Now, just like exponential functions or expressions have rules, so do logarithms, and they are very similar. So we're going to start with the product rule for logs. The product rule says that if the argument of the logarithm, in other words, the input for the logarithm, involves multiplication, if it's a product, then you can break that up to be the addition of 2 or more log expressions. Now notice that all of these expressions have the same base. You know, you couldn't do much with exponents unless they had the same base. And that same is true of logarithms. Make sure that you note that in your notes somewhere. So let's look at an example. Here we're going to expand a single logarithm into multiple logarithms. So we have log base 5 of 1,000. Now that is equal to log base 5 of 10 times 100. 1,000 is definitely 10 times 100. That means we can write this as log base 5 of 10 plus the log base 5 of 100, because the product rule says anytime I have multiplication here, I can break that up into 2 logs that I add together. Let's look at another example. Now, in this example, we're going in the other direction. I started with individual logs that had the same base, and I'm adding them. That means I can rewrite those as a single logarithm or condense them into a single logarithm with the same base, and I can take those 2 inputs and multiply them together. So sometimes you'll see this as condense into a single logarithm. You might see that, but here I'm going to also call this simplifying. So I have the log base 5 of 6 and the log base 5 of 5. Now, it satisfies the requirement that these both have the same base. I can combine those to be the log base 5 of 5 times 6, or, in other words, the log base 5 of 30. Pause now and copy down everything on this slide. Next, we're going to look at the quotient rule. And you may have guessed that this involves division and subtraction. It says that if the input into the log involves division, you can break that up into 2 logs or more logs that you subtract. So in this case, we have the log base 3 of 6 divided by 2. We can rewrite that as 2 separate logs, log base 3 of 6 minus log base 3 of 2. Now note that the bases of these have to be identical or this will not work. Let's look at another example. Now in the first example, we expanded a single logarithm into 2 separate logarithms. In this case, we are starting with separate logarithms and we are combining them or condensing them or simplifying them into a single logarithm using this same rule. We see that we have subtraction here. A log base b of m minus log base b of n. That means we can write that as a single logarithm, log base b of m divided by n. And here is an example. We have log base 3 of 4 minus log base 3 of 3. We can rewrite that as log base 3 of 4 over 3. Now the power rule is very similar to the power of a power rule for logs. It says that if I have an exponent on my input for my log, that exponent can be rewritten as a multiplier for my entire log. Let me show you an example of that. If I start with log base 5 of 10 to the third power, that is equal to 3 log base 5 of 10. Here's another example. Log base 10 of 5 to the second power is equal to 2 times log base 10 of 5. And that works the other way around too. If it started out as a multiplier in front of a log, I can move it to be an exponent of the input of the log. So if I started with 3 times log base 5 of 10, I can rewrite that ultimately as log base 5 of 10 to the third power. Here is another example of that. Pause now and write down all of the examples on this slide. Now I just have a few more things to cover with you. One is the change of base rule for logs. Now the default is base 10. But if you don't have a calculator, or if all you have is a scientific calculator or an older calculator, how do you evaluate a log that has a base other than 10? Well, you can use it by converting it into a fraction of this form. Log base c of m divided by log base c of b, where c can be any base that you select. And I would advise you to always make that log base 10 because there is a log key on most calculators. And anytime you see log, it is base 10. So if I needed to know what the value of log base 5 of 3 is, I could, using any calculator that had a log key, put in log of 3 divided by log base 10 of 5. And I don't have to worry about putting the base in because the default base is 10. If I want to simplify that, go the other direction, I can rewrite a log that I find in this format as a single logarithm, log base 2 of 5, because I know that whatever the input is in this denominator, that's my base. And this is my input. Now, another case I want to talk to you about is the case where logs have the same base. If I have this situation, log base b of m is equal to log base b of n, then m, Mary, is equal to Nancy. Here's an example. I have two logarithms on both sides of the equal signs that have the same base. Therefore, 2x is equal to 4, and I can go ahead and solve for x. Please pause now and note everything on this slide. And last, I want to talk about the inverse of Euler's number to natural log. Now, suppose we had this situation. We have an exponential expression, but it involves e. Well, I can rewrite that as a logarithm, log base e of x, using the same rules as I used for exponential to log. And I can also go in the other direction by using the same rules as log to exponential. Now, I want you to pause now, note everything on this slide. Hopefully, you've also taken some notes about some things I've said. Come to class with questions.